Good morning and welcome to this next lecture on sound and structural vibration. We had reached up till this point where we found coupled roots using asymptotics for m less than 1 and greater than 1. So, this is the picture we have now. Okay. Now, today I will give a brief explanation on the or a discussion of the roots. Discussion on the roots. Now, the denominator, okay, the denominator in the dimensional form is given by k fourth minus kp fourth into square root of k square minus k 0 squared minus mu kp fourth equal to 0. Okay. And gamma is equal to square root of k square minus k 0 squared. Okay. And gamma square is equal to k square minus k 0 square, which implies k square is equal to gamma square plus k 0 squared. Okay. So, if we write this denominator in terms of gamma, so what we get is gamma square plus k 0 square whole squared minus kp fourth into gamma minus mu kp fourth equal to 0. Okay. If we open it out, gamma fourth plus twice gamma square k 0 square plus k 0 fourth minus kp fourth into gamma minus mu kp fourth equal to 0. Okay. And so, this becomes gamma fifth order again plus twice k 0 squared gamma cube plus k 0 fourth minus kp fourth gamma minus mu kp fourth equal to 0. Okay. Now, for some value of the parameters, for some parameter values, does not matter. So, we have for m less than 1, m less than 1, a root at gamma 1 and a root called gamma 2, a root called at gamma 3 and gamma 5 and gamma 4. Okay, we get these roots. And similarly for m greater than 1, for m greater than 1, we get a root at gamma 1, then we get gamma 2, gamma 3 and gamma 4 and gamma 5. These are the roots we get. Okay. Now, what's the thought process here? If you recall, we said that this gamma is a square root function k square minus k0 squared, and therefore if we do a complex contour integration, then we have to choose a continuous branch for gamma, and so the branch cuts coming. Okay, so if you recall, I have shown you a cut where the cut is between k0 and minus k0. I have shown you another where the cut extends from k0 to infinity, minus k0 to minus infinity. Okay, I have shown you a cut which is an L-shaped cut. So I come from k0 just above, go vertical. I come from minus k0 just below and go down vertical. This is an L-shaped cut. And I also shown you a cut which goes from k0 to plus I infinity, minus k0 to minus k0 minus I infinity. Okay, I've shown you. Okay, so these are first of all branches where the gamma is continuous. That means what? Just to show you, I have to have the real line integral. Let me take blue. For this case, I come from minus infinity above, get on to the cut, cross here, get down from the cut, go off to infinity, come over all the way at infinity, hit this line, go vertically down, go right, go round the cut, get down below, cross here, come here all the way, and from infinity I join. Okay, there is a sign change of pi over here, so I can't cross. Okay. Similarly, on this picture here, on the picture on the right here, if I take an integral, I'll come all the way above the crossover, go below, go off to plus infinity, come on an arc at infinity, and this is a cut, so I cannot cross. I come down, I go round this branch here, go up at an arc of radius infinity, again come down and join. Okay, so this is a closed contour and this is a closed contour which we need for Cauchy residue theorem. Okay, we need this for the Cauchy residue theorem, and after going around closed contours we look at singularities, isolated singularities. and compute residues. Okay. So finding a continuous branch is one point. The other was causality. Causality had to be maintained. Okay. That means if gamma is a real number, it should be a positive, okay, real number, okay, when k is real. Okay. Similarly, gamma, if it's imaginary, it should be negative imaginary, again when k is real. Okay. So now with these restrictions, what did we do? We looked at square root of k square minus k0 square, and we found it was magnitude k minus k0 to the power half, magnitude k plus k0 to the power half, and now this angles phi plus theta by 2. So this gave a gamma definition, or this gave me a gamma plane that corresponds to k plane. Okay. That means if I am moving, let me just take the last cut. Okay, the last cut is here. So if I am moving here, I'm crossing, if I am moving here, and then if I go off at infinity and come here, and I am moving down the cut, okay, going around the cut, if I am moving in this manner, how will I move in the gamma plane? Using this definition of k, how will I move in the gamma plane? Okay. So it turns out I will move in the gamma plane in this fashion. Okay, I will move, this is my gamma plane, I have to be on the right here to the gamma plane. Okay. So now what roots did I get? I got a gamma 1 root, I got a gamma 2 root, I got a gamma 3 root, and I got gamma 4 and 5 roots for m less than 1. Okay. For m greater than 1, for m greater than 1, let me do that. So I will get, let me do it separately. For m greater than 1, I will get again gamma 1, I get gamma 2, I get gamma 3, and I get a, let me write it closer, I get a gamma 4 and a gamma 5. And again, if I am moving in this fashion in the k plane with this cut, I will get a region in the gamma plane where I have to be again to the right here. Okay. So that means now these are the gamma roots that are valid, whereas these are the gamma roots that are valid, because they obey the causality. They obey causality. Okay. So now this one story. The other story is that instead of this cut which has vertical portions, if I take the L cut, okay, if I use the L cut, I use this L cut over here, okay, and this is of course the K plane, right, this K plane, and move to the gamma plane. If I move to the gamma plane, then my gamma plane happens to be to the right of this entire region, which means what? My gamma 2 gets included, gamma 2 gets included, gamma 1 gets included, gamma 3 gets included, okay. So now there is a slight difference based on the cut, based on the cut, based on the cut, the valid gamma roots change, okay. What does that do? That changes the singularities, that changes the singularities, okay, and therefore it changes the residue contribution, okay. So now there has been a discussion on this. If you look at the literature, okay, the originator is of course D.G. Crichton. His work is the starting point. Then there has been some discussion by authors like Stewart and Stroderman and his co-workers. You can look at that literature. So finally we will go with what Crichton says in his Rayleigh medal lecture. It's interesting if one can read and follow that literature, okay, but as a introductory course it's best avoided at this level. So finally we'll go with what Crichton says, and Crichton takes this cut, okay, Crichton uses this vertical cut, and what he says is that there is always a subsonic root, K root, okay, and it is that K is near Kp for m less than 1, and that K is near K0 for m greater than 1, okay, and then for m greater than 1 there is a root K, okay, which is near Kp plus a small damping value, okay. So this root now, as it moves on the plate, it starts to decay away slowly, okay, and because this is supersonic now, this root is supersonic, okay, because Kp is less than K0. Okay, it radiates sound, it radiates sound. It radiates sound, but and the sound radiation goes up in the y direction, it goes up in the y direction. Okay, it increases in the y direction. It's a little counterintuitive. Okay, however, if this is my plate, if this is my plate and this is my line forcing, it may be increasing this way. Okay, but as this happens to be the origin of the entire vibration and sound, okay, and the propagating wave along the plate is decreasing. Okay, so a little to the right the vibration has decreased and the sound field grows. Okay, a little further to the right the vibration is further decreased and sound field grows. Okay, but if you look at a line originating from the forcing, a radial line, okay, you will see that the sound field is decreasing. The sound field is decreasing. Okay, so we will follow, and he says that different cuts produce different valid roots. Okay, but you will find this root that is subsonic always, okay, and any other root you find based on your cut. Okay, in the far field will have negligible contribution. Okay. So now I'll just give you what we are going to do. Okay, I'm running out of time. So in the next class I'll just summarize the roots. That means their expressions. Okay, that's one thing. Then there are regions for values of epsilon and m where the original okay, roots are not valid. Original expressions here are not valid. Okay, so we will find new expressions. Then for some values expressions cannot be found using asymptotics. That means what? New roots of k, right? New roots of k as a result of fluid loading are not small perturbations. They are not small perturbations to original roots. So they have moved far away, and this region we call it as significant fluid loading. The fluid has loaded the structure enough that the original in vacuo roots are shifted far away and cannot be found using this perturbation method. Okay. So we will find those regions. Okay. Then we will examine this denominator which I said represents structural stiffness, structural inertia and so forth. So we will change the values of epsilon and m, and we examine which of these physical factors are dominant in which regions in frequency. Okay. Somewhere structural inertia will be dominant, somewhere fluid inertia will be dominant, okay, along the frequency axis. We have the frequency axis going from 0, non-dimensional value 1 and above, right. So we will see which of these dominate in which regions in frequency as we move along frequency. Okay. Now we have given the velocity field, coupled velocity field we have given. If you recall, we gave it as the residues times, added with V1 plus V2. So V1 plus V2 we showed as a dominantly e to the power ik0x with a decay in the x direction, but we did not give the residue contribution. The residue contribution will be straight away given because we now know the singularities. Okay, based on Crichton. Okay, so based on Crichton's analysis. So these singularities will contribute residues. So what will be left then is the coupled acoustic field. Okay. So with this I close this lecture. We will continue in next class. Thanks.